Okay, can you tell me where the boundaries are?
Yeah, you're live already. They hear you.
They can hear me?
They could hear you. They are hearing you.
They are hearing me?
Yeah.
Do you want to, can they hear you?
I don't know.
Hold on, man.
One boundary.
I'll do it.
Continue. Continue. Your face is in the way. Continue. There.
Okay. Oh, so where I had it before, you told me to erase it.
That is not where you had it before.
Well, it was like a little over here.
You're live.
I am, okay. Now we're just discussing where the boundaries for the video are. So, no, but thank you for showing up to today's beginner lecture. Before I begin, we're gonna put leak code questions up soon, on this topic of trees. On top of that, I will say do sign in. It's right here. I don't know if I was being blocked by the QR code. Am I being blocked? Okay, because you're not there. Please, Lazaro.
You know you're fine.
Okay.
You pointed exactly at it.
Okay, good. Oh, so you're looking?
Yeah, but it's delayed, so it's like a good 10 seconds.
Okay, all right. But do sign in with the QR code and the Airtable. Well, that's gonna be on the QR code. Additionally, be sure to, if you can, attend the GitHub workshop tonight at 7:30, I believe. Is it, Laz?
Mm-hmm.
It's at 7:30, right?
Yes.
So yeah, GitHub workshop at 7:30. Be sure to look out for that. This Friday, when did we have the binary search night? It was this. Okay, so no binary search competition this week. And yeah, so yeah, let's get started. So today we're gonna talk about trees, right? So. Right. So while they're taking care of that, we're going to discuss what a tree is. So basically we talked about what a linked list is, and now it's just nodes linked up together like this. That, we're not going to do, this is two nodes, one node points to the next one. And then we also discussed doubly linked lists, but that's, that's kind of relevant, but not exactly what we want to discuss. So that I would say that the nodes we talked about before were list nodes. Now we're going to talk about tree nodes. So I'm going to define a class, tree node, right? And leak code kind of defines it for you too, when you're doing problems like this. Do the constructor. And then, I'm going to say so value equals 0. And so the tree node has, actually, let me bring it down a little bit more. Okay, it has a value, like the list node we talked about has a value. And it has 2 children. Particularly true. My mistake. We are talking about binary trees, because a tree can have more than 2 children. But in binary trees, binary is the key word. It's 2 children. So, now val. Self has a left child equals to and it has a right child, and I will put left here. By default is none. Hello. So this is the tree node, right? The constructor. I put the value by default is 0. The left child, which is another tree node, is none, so it's null by default. Same goes for the right. And so it kind of looks something like this. So let's say I initialize tn equals tree node equals okay. And another thing, this tree node's values are specifically ints, right? So that's just, it could have been a string. Remember, in a node, the value could be of any type that you define. And so if I do this, what does that look like conceptually? For those that have exposure, how would I draw this?
You would have like one node.
Yeah, you would have one node, right? One tree node. It's right here, right? And what are the attributes of this tree node?
3, none.
Okay, 3, none, none, right? So let's get the left child, which by default is none, so none, but I don't really have to write it, just empty. And then the right is also none, so it's empty. So that's this. And I can do tn2 equals uh, 5, and I say what about now? Yeah. The left child is what? Of tree. Okay, and what is it?
5.
Right. Right. And by default, I said there were none. Okay. And I'll do another one. And then equals. What about now? What happens now?
The right branch.
Of which one? This?
Of the child.
Yeah.
It's just 0.
Yeah, because of the default, right? I defaulted it to 0. I didn't pick any value. So, of course, well, this is conceptual. So you kind of just know that. Sorry, Laz. That was loud for you. That they're, typically we don't represent it like this, right? The extra arrows, we kind of we know they're there, right? So also this kind of does save some space, rather than just having it all, sprawl out. But anyway, I'm gonna erase this and that. So that's that's the basics of a binary tree, right? And the key thing is binary, right? If I wanted to define a tree node that could have n array, so any variably sized amount of children, how would you define this class? I'm gonna do it here. Call it n. Oh. What other argument should I put for an NRE?
There'll be arcs, like asterisk arcs.
Asterisks. Oh, Um, no, it's an easier way of doing this, right? What if we just had a list?
Like a list.
Yeah, so you just have a list. I'll call it nodes. And by default, I'll make it, you can do this. Okay, empty list. Right. And I would say dot val and self. Well, I would say children. Let's call them children. Because they're children, right? Self.children equals children. So here, well, I'm not going to initialize it, like, with code, but I'm just going to start out with this, right? So I can have a 6, and this could be a 3, could be a 5. But since it's n-ary, it's a list, right? I can add as many as I want. Eight, 1, right? So because I didn't put left and right, I'm no longer confined to just 2 children in n-ary, right? So that's the difference between binary and n-ary trees, where binary is just 2 children per each node at most, and then n-ary can have as many children as you want. Of course, you can define a constraint where you can have like a max children amount, right? So that's like maybe 5 or 6, but I'm not going to get too much into this because, I just wanted to discuss the difference between n-ary and binary trees, which is just that. But, today's lecture is just focused on binary trees. Well, actually, the n-ary does come into play with this next, tree traversal algorithms that we may choose. So I'm just going to stick with this. So I'll define an arbitrary tree. Okay, all right. So how do we traverse a tree, right? Anybody know what they should do to traverse this tree to say print out the values in a certain order? Okay. So we talked about recursion the last time, right? So recursion basically means that the function is calling itself, to achieve something. So we could say, so there's 3 different types of ordering to, go through a tree. So the first one is, well, I'll do in order first. So there's in order, and in order takes in a node, so I'm just going to call it node, right? So what does in order do? So it checks that node exists, right? If the node is not none, then we could say print node.val. Okay? And in order basically does the parent first and then the children, particularly in the order of parent, left, right. So after you print node value, you would recursively call in order on node.left, node.right. Okay? So let's say I called We call this one root. Root. How's that gonna print everything? Oh, and where is it? End equals, now it's complicated, but so I'm just saying that at the end of each, just instead of doing new line, you just put a comma after the number. So what's the order? So how is it going to print out the values in this tree if I call this?
Well, how does it traverse the tree though? Oh, okay, I see.
Yeah, because you're going to go to the left and then come out, go to the right.
You're gonna print out the whole left branch first, and then the right one. Like 1, 2. What's that?
That is
1, 2,
DFS.
4, 5, 3, 6, 7. And no, 3, 6, 8, 7, 8.
This is pre-order. This is pre-order. This is pre-order. My mistake. This is pre-order. Yeah, these mistakes. Right, guys. Pre-order. Yeah. So it does this, and then the whole left, and then the whole right. So what's the? So I'll just start it off. And what's after that? 2. Okay, yeah, 4. Yeah, no children. What's the 5? 6, 8, 7, 9, 10. Okay. All right. So that's the pre-order way of doing it, right? So, is it 1, 2? Yeah. So it's the root, and then everything to the left, and then everything to the right, right? The subtrees, I mean, the left and right subtrees. So 1 was first, and then we go left, and then 2 was the parent of everything here. So that was before, and then 4 was the parent of nothing, and then 5 was the right of 2, and 5 is also a parent. So it also falls in line. And if no is null, nothing happens. So that breaks the recursive call. Okay, so now that was pre-order. So let's do post-order. Okay, so how is post-order different? Does anybody know?
No is at the end.
Yeah, right.
Well, the root.
Yeah. You get the root at the end, right? Let me erase this. Print node. Okay. And change this also post. Okay. So I'm gonna call that a root again. So what about then?
Wait, what's your question?
Yeah, what does this print out? Like what ordering of the numbers?
Starts with
2?
But isn't it? Wait, left, right, and then root. So it would have to start on the left side and then the right side.
Okay, yeah. So we would go to 4, right? All the way to the left. Then you go up, yeah, and then 5. And you go back up, right? And then you print that node. 2. Okay. And then it's 3. No, it's not 3. It's not 3. Yeah, 8. and then go back up. There's no right, so it goes straight to node. Go back up. There's a right here. It's not 7 though. It's 9. You have to go all the way down here. Under 7. Into 3. And into 1, which is roots. And of course I have to do this because I ended with a comma. Yeah.
So the recursion, it's gonna keep like looping through it until the node is empty.
Yeah.
When the node is empty,
You
it
just
will actually go back up.
go back up. Yeah, go back up the recursive stack once you've reached the base case.
So isn't that really slow though? Like
No,
it's
it works out. It works out. I mean, yeah, there's like some things that happen on the machine that might make it slower than, say, going through a for loop, which we will actually go into, but in a little bit. So this is the post order. Now, what about in order? So, which one's in order?
Left, root, right.
Right. So I'm gonna erase these two. They can read these letters, right? On the screen?
Yeah.
Okay.
It's much closer now.
Okay.
For your if node, right? In Python, you're just verifying if like the
Yeah,
node is not known.
it's not no, or not none, or you could put if not node is none, or equal, but then at that point you could do that. But if node is just checking all those things, so that's just a convention.
So how you had it is like the correct syntax, or is that like pseudo?
No, these are all correct ways of checking the same thing. This is just like the more succinct, less verbose way of doing it, which I think it's preferable. All right, so let's go over in order. Actually, now that I think about it, I should have relabeled these numbers. Yeah, I should have relabeled these numbers. Yeah, it doesn't matter, whatever. All right, so what is this print?
4, 4, 2, 5, 5. Then 2 at the root. 1.
Well, 2 is the root of this one.
I'm saying the root out of the entire tree. Is that a 2 or?
That's a 1. That's a 1. My bad. I erased it. So what is it? 8, right? 6. 9, right? You have to go all the way left. Then 7. Then 10. Okay. That was the in order way of traversing. So 3 different orderings, but they give you vastly different results, right? So, oh, you solved it? Lazaro solved it, guys. Can we get an applause for Lazaro? All right. So there were 3 different ways of doing it, and this path that we took, I'll do it blue. It's like this. Well, you've actually reached the end at that point, right? That's the path we follow. And here we have to get all the way to the left, right? Then go back up to the the parent, and then go all the way to the right. And maybe to the right, maybe you have to go all the way to the left as well. Like in this case here, when you're going to the right, since this is, a case, right? You may have to go all the way to the left too, which is this part. Does that make sense? No? Armes, you have questions?
Do you think you could go like just through one of the branches by saying like, okay, at this point at the code or at this node?
Okay, so here, oh my God. So this is the right child, right? But this is a node who has a left. So that means that we're going to go all the way to the left for that. And then we're going to go here, right? Like basically we're here and you want to do what we did here, do all of that, for the subtree, then do the root or the parent, and then do everything we did here on the right subtree. So it's kind of like this, right? 1 is the parent. And then what we're going to do to 1, we do to 2 and everything. And then once we did 2, we add 1. And then what we ever did in 2, we do to this subtree recursively. Does that make a little bit more sense?
Yeah.
A little bit? All right, yeah, this is a bit recursive stuff here. Oh, by the way, is this DFS or BFS? Way of traversing this tree.
DFS.
Why is it DFS?
Because you're going all the way down.
Yeah, because you're going all the way down the depth, right? And then you're doing whatever you need to do. You go all the way down, and you backtrack up, and then you see there's more. You go down that depth, other path, right? So you're going all the way down, and once you've reached, the base, the bottom, you backtrack up and see if there's any more paths. That's the basics of DFS. So this is all the ways that I did it. That was all DFS, right? Because you're going down the depth of the tree. So what about? Well, I'm gonna just erase this. And I'm going to erase this one too. Okay. And I'm going to, DFS I use in graphs in general, but, it's good to use them in trees too. Okay, so let's use DFS to, I'm going to use a different color. Oh, wait. Let me give it values. Call this. It doesn't matter. Okay, so how do we traverse this tree using DFS? Any ideas?
Well, yeah, just
DFS. Kind of the same way we did it before.
Just all the way down, starting from the root.
Right. Well, since it's just a tree, we don't have to color the nodes. Although, I'll go over DFS again once we go over graphs, right? Really briefly. Although we did kind of talk about DFS before. We did do that. But for the sake of this tree, I don't have to color code any nodes, which I'll get into why we do it in graphs. And the main reason is because we might run into this or this. That's why we would color code it. But since it's just a tree that goes all the way down, we don't have to worry. So let's do DFS, right? So
I have a question.
yeah, you have a question?
Yeah. What type of graph is a tree?
It would be a
Type of graph. is
yeah,
tree.
right.
That doesn't make sense.
Yeah. No, it is a type. So, what kind of graph is well? Then again, if it's directed like this,
Oh,
isn't that still acyclic?
Yeah, but I think trees are undirected now.
Hmm.
Like there's
So
only
at that
one
point-
path to get to a node.
There isn't a cycle. So
There's
Yeah.
right.
So it's acyclic. But
This is acyclic, right? So there's no cycle. Well, here there is no cycle either. There is no. There's kind of a cycle, but since it's directed and they're all going to 4, it's not a cycle. But he's saying that if it was undirected, we'll see. That's the thing. That assumes that this is adjacent to this. But in a tree,
yeah, but John asked Geary if a tree is a type of DAG, and I think Geary said no.
it's a type of what?
DAG.
DAG.
Directed acyclic graph.
If a tree was, he said no. Geary
I
said no.
think he said no.
Am I saying no right now? I think I'm saying no, too.
Oh, you're saying that it's directed. So you're saying that it is.
Well, I'm saying it's directed, right?
Okay,
This
it's
is
acyclic.
this is an acyclic graph, guys. This is acyclic. There's no cycle, right? And because there's no cycle, we don't need to color code anything. But in a graph, you may find cycles. That's why in both DFS and BFS, you have to color code your nodes. We're not going to do it, but let's just say def DFS the tree. And this time we're working with n-ary tree, not a binary tree. So what do we do? Oh, and I guess I'm gonna say in order. In order.
Are we assuming we already created the class?
Actually, now that I think about it, in order doesn't make any sense. We're gonna do pre-order. We're gonna do pre-order.
What's pre-order? Left, current, right?
No, what's pre-order, guys?
Root left,
Huh?
right. Root left, right.
Root left, right. But here, what would it be?
You said we're doing pre-order for that one?
How
Yeah.
can this orders matter if it's not binary?
What do you mean?
You're saying like go from left all the way to right?
Yeah.
Is that how you want it? Read left to right?
Yeah, just,
Yeah.
I guess you're kind of right, but that's the thing. When do we get to this, right? There's 3 children now.
I think you can do it.
How?
You're gonna get the children of the current node, do it for loop. If you're gonna do left first, iterate from left to right, and the children are right.
No,
What do you mean no?
no.
Are you sure?
I feel like that's gonna complicate things when you want to get the thing in the middle. Where's the middle of this? Do I do it after
I'm not
5 or
doing the thing
before
in the
5?
middle. I never got the thing
That's the
in
thing. If we're doing in order, it has to be somewhere here, right? In the middle of the for loop, I have to
What's
print the
in order?
value.
What's in order? I don't know the traversals. What's in order?
In order.
What's in order, guys?
Okay.
Left, root, right.
The root, then left and right?
Left, root, right.
Oh,
Root is in the
left,
middle.
root, you can't do it in order.
Yeah, that's what I'm saying now. We can't do in order here. We have to do
Wait.
either pre-order or post-order.
Wait. Sure?
I mean, I guess I
What
could
if you
just.
get half the children list?
Yes, I was thinking of doing that, but that's gonna complicate things.
Okay, we can talk about this later.
We'll talk about this later, guys. So either pre-order or post-order. So I'm going to do
Let them
pre-order.
decide.
Okay, guys, what do you want to do? Pre-order or post-order?
Pre-order.
Okay. Well, that was one voice. No order? All right,
No
so can we
order.
just not do it? Let's just not do it? Okay.
That's
All
actually
right.
a good idea.
Yeah, let's just not do it, guys. What's up? How's it going? No, I'm just kidding. So we're going to do pre-order DFS tree traversal. So that means that the children come before, well, no. The root comes before the children. The parent comes before the children. So I will print the val right? And then, what would I do? Well, what did I say about n-ary tree nodes as opposed to this one? What was the difference?
They have a list.
They have a list. So you do a for loop for I'm gonna say node n in C. Do C. For C in it's an attribute of node. Right? This is how you do for loops. Iterate through each child in the list of children of the node. So for each, you actually have to call the function again. C. Okay. And that's it. So what is this is DFS in preorder root. I'm saying this is root. How does it print the values? Yeah, 3. And then yeah, 2. Yeah, you're right. All right. Okay. 9, right? 10, right?
Can you rewrite that?
I actually do need to rewrite that.
No, like the 9 and 10 because I can't see on the screen. Like in the live stream.
I actually need to rewrite this function. Oh yeah, I didn't check for something very important. I did not check for
The
something.
if node.
Huh?
You need the if node.
The null, yeah, the null. Who said the null? I didn't check if it was null.
Wait.
Yeah.
Initially, the node that children list is empty, so it wouldn't. Would that be an issue? I don't think so, right?
I
You
mean,
just put it into the for
that's a good point. I mean, it's just good practice.
Yeah, but okay. Yeah.
I get this part right. So basically, this for loop will only run if this is a filled, right? So by default, node, n-ary tree node may have an empty list of children. So if it's empty, it won't run it. So it will not run an empty node. I just still think it's best practice just to put it here. My mistake, guys.
Python, is that like an error though?
Kind of. It would, because let's say I put in something here and it's not set. But then again, you can't really put in a none.
Oh, I see the issue. The issue is you might call none.children in the initial call. Your root is none.
What?
That's the only issue.
Yeah, that's what I'm saying. Oy vey. If node. Just pretend I wrote it up there. What I had, it's here. I think I can fit it in. Can I get a time check, Lars?
You're 44 minutes in.
Okay, we're good. All right, bright if node. So, okay, what else? Is there another order I could have done this in? So this is pre-order. How is post-order again?
Start from the bottom.
Left, right, root.
Yeah, the bottom. Left, right, and then the root is last. So 1 was the last one. So what's the only difference I have to do here?
Move the prints.
Yeah, to the bottom, right. So just move this print to the bottom and it's post-order. So in a way, so it was a little simpler in writing. Well, I don't know if it was simpler in writing. Do you guys think this is simpler in writing, or do you think the other one was easier? Just show of hands. The other one? The other one? Okay, what's your question?
So, does it matter the order that the list of children far in?
I think it's just set. Like I think I get what you're saying, because this could have been called first, right, in the list. I think the way you draw it by convention, right? This is left to right, so this is the first child, right, and then this is the last one. That's just kind of how I guess I would draw the map. I mean, I could have done this, right? Right.
And the code would still run the same.
Well, let's say in the, like, I drew it like this, but in the code, the list of children is actually 254. So it would call this before this. But when I draw the data structure, right, I'm complicating things. I know, Lazaro.
No, not even that. Like,
What? What?
I don't think the order matters because you would draw the tree based on the children.
It's just like the children. Like you're gonna call the root first. Well, I mean here not, but the other one. And then you would go by children in any order. I mean, the ordering doesn't matter. You're right. I mean, the children could be ordered anyway. The important thing is that you're doing the root and then you're doing the children, right? So you're recursively calling the function on each children that it has. And it could be an n amount of children, any amount, like this, right?
So the print statement won't change. It'll always be in that order.
Oh no! We did this already, right? Well, I put it here, so it will change. So let's do this one, right? So how does this one go? 1, right? 6. Yeah, I know. 2. Right. And then, yeah. And yeah, we're assuming that this is to the left of 2. And then 4. No, not 4. 7, right. 8, 9, 10, 4, and then 3. So vastly different. The ordering was vastly different because I put the print out after the for loop, which recursively calls each child. And it's also possible that it has no children, so it's empty, so it just prints it by itself, which is this case for 1. There's no children, so it just prints the 1. All right? Okay, so yeah, that's DFS n-ary tree traversal. I'm going to keep this one. So there's a different algorithm where it does not recursively call on the tree. So which is that one that I discussed before briefly?
BFS.
Yeah, BFS, and which stands for
Right.
breadth for search. So it takes it by level, right? So I'm just going to show you first how it's going to print. It's going to, yeah, go ahead.
Can you do DFS non-recursively?
Can I do DFS non-recursively? Isn't that just,
Like it,
can you?
Like in a while loop with another data structure
I don't think so. Can you?
with a stack? No, it's the same thing. In a while loop,
Hmm.
you append the children and you call.
You append, oh, while left, while cur.left equals, and then you pop, and then you go back, and then you go to right, and then you do the same while left, and pop, and then right. I guess you can. I wasn't. How much time do I have left?
Not enough for that.
Not enough for that. So no, Lazaro. I'm sorry. Well, actually, I
Well,
want
you
to.
could,
I could put it in, but I'm not gonna.
Homework.
Homework, guys. Figure out how to do DFS non-recursively with a stack. For a binary tree. For a binary tree. I don't know. How do you do it with the
For loop, the same thing.
with this?
Yeah,
Where do you go?
for loop. Like you iterate over the children and then append to the
Okay.
stack.
Well, BFS is much simpler than that stack DFS stuff. All right. Well, where you use a stack for that DFS stuff, which is kind of the same here. You're kind of, you're doing it's much like pushing this, then pushing this, then pushing this, then popping that, then pushing this, popping that, pushing this. Okay, I'm not going to get too much into that. That's confusing. BFS, right. So how does BFS work? Level, like I said. So it's going to go like this, then like that, then like that. So I already know that the way it's going to print, I don't know if the numbers are still clear. 3, 2, 5, 4, 1, it's a 6. I smudged the numbers, so might be hard to see. Okay. So that's the order of BFS, right? So what was the key thing that happened?
Left to right.
Root, okay.
Mm-hmm. Yeah, well, root left to right. So I'm going to call this L1, L2, L3 is all this. L1 is just this one. L2, and then L3. So right. So they're ordered by their levels, right? The highest level is first, then the level beneath that one, and the level beneath that one. And these are multiple nodes, and I was saying, what is it? The children for this are here and here. This has no children. The children for this are here and here and here. All right? So how do we order it like this, by level? How does that get done? Where the nodes in level 3 could be the children of any of these.
You can print the node value and then
Yeah.
do a for of the children and call the function. Like,
See, that's the thing. We're not going to call the function again. This is done non-recursively. So what could we do? So there's this data structure. I went over queues. I did go over queues. Do you remember when I went over queues? So a queue is kind of like a stack, except you add to the front. Well, you add to the back, right? But you take from the front. So it's like a line, a queue. They go in through here, they come out through here. Whereas a stack, they go in here, they come out here, right? So basically, in order to get this one out, you need to get out all the ones that are, on top of it. And these came after this. But here, I could put this guy here, this one here, then this one comes. But the first one that came is the one that leaves. So on and so forth. So what if we did this? So I'm going to define a queue. And lists can have queue-like properties in Python. So it's going to be an empty, right? And roots, I'm going to say queue dot append root, right? And I don't need to color code it. If this was a cyclic graph and I had something like this, I would need to color code it, but I don't need to because this is a tree, right? This is directed. This is acyclic. But no, Gary said it wasn't a DAG. So first we append the root, right? While queue, right? So while the queue still has elements in it, we can do work on it. So we can do current node equals queue dot pop. Well, actually, no. You don't pop from the end. This is popping from the end, like a stack. You pop from the beginning, right? So I'm gonna do it like this, right? So cur dot equals q dot pop.
Is it pop or is it like on Q?
Well, I appended it here. This is the NQ. I appended the root.
Oh,
That's-
Python is different.
Yeah, this is different. This is the NQ, and then this is the DQ from the front, or from the left, right? Oh, yeah. So that's because that's the beginning, pop 0. And of course, this will work. 0 is a valid index as long as Q is not empty.
Wait,
No.
Like time complexity wise, no. It should be pop left, and instead of using to array,
Yeah, this is the left. This is the leftmost.
time complexity wise though it's wrong.
Is it a Python thing?
And pop 0, it
Yeah.
wants to move every other element within the array, so that'll be n squared right there.
Okay, so what do I do?
Pop left.
That's the thing.
Yes, but not for arrays. You need to import DQ.
Import. Okay, so Lázaro is gonna help me with this. So
Just so like we can get time complexity to open.
okay, import
Python doesn't have built-in queues, data structure. So you
deck
import DQ.
deck from where? From collections.
I think it's from collection.
From collections.
Wait. Oh,
I think it is, right?
I think so.
Okay, so Q equals
Yeah, I think so.
like that, and then Q dot push. So now it's push, right? Push to the left. I don't need to specify, right? No, is it NQ? Damn it, you made me do this, Lázaro. I was just gonna do that.
Just a pen.
It's just a pen?
Yeah.
Okay. And then pop from left is just that thing. So append root while Q, right? Cur equals Q dot pop from left. How do you?
Just pop left parentheses.
Is it just no underscore?
No, do it again.
Right. Okay. So yeah, we just did this because you told me that in a Python, native list is gonna be really slow if I do pop 0. But no, yeah, you had the right idea to pop from the leftmost value. So you pop from the leftmost value, and this is a node, right? Which has a list of children. So, well, we could print it like we did before. Val equals, right? Then for C in dot, right? I'm gonna erase this. For C in cur dot children, is it Q dot append C. All right. So, and of course you don't have to put any colors on it because this is directed and there's no cycles. So, how do you think this one will work? So let's say we're going to use this as our Q, right? So what happens first?
so you plug in the root,
Right. So I'm just going to plug in the value for root. So,
you plug in the root's children until
Right.
there's no more.
so yeah, so
Then you pop
first
the root.
I pop, right? So I get rid of it.
Oh.
But I have the list of children, right? Which is stored in cur. So I add his children, which is 2, 5, and 4.
Right.
Okay. So then I'm done adding the children in this for loop. I go back and I check if Q is, not empty, and it's not. So we can still do work. So then I pop from the left, which is 2, right? And I get 2 children, which is 1 and 6. So I append the children. So 1, 6. All right? Yeah.
So why do you pop it out first?
So basically, the point, well, you have a point. I could pop it at the end.
Yeah, that's what I was thinking. Because if you pop it, do you even have access to the children? Like once you pop it?
Is the peak, there's a peak left, right? Is that what it's called?
Wait, what's the question?
They're asking if I could pop it. I mean, that's the thing. It's a node,
Yeah.
right? It's a value, right? And that value is going to have its attributes still, even if I popped it from the queue. But they're asking if I could simplify it by leaving it there, adding the children, and then popping it out, which we could do that. I mean,
Yeah, but why not pop it?
is this confusing to do it first? Do you want me to put it at the end?
It's whatever.
It's whatever.
Convention like that.
Convention, you pop it first and then you add the children. So I keep adding it, and then I pop 2. Then I go back, check if it's empty. It's not. 5 is there. I pop it. And then, did it have any children? No. So that means that there is no current children, so it skips. So now we have a queue with less values than before. So that's the thing. Once we reach the leaf nodes, that's when the size of this queue starts to diminish. So check it again. Yeah, it's still there. So then you pop it. You pop 4. What were 4's children? We're 7, 8, 9, and 10. So 7, 8, 9, and 10. And then we pop 4. Now we check. Again, we're done adding his children. We come back here to the queue. Check if it's still not empty. It's not empty. So now we just keep popping, right? So 1, pop 1. No children. We don't add anything. 6 here, pop it. No children. 7, no children. 8, no children. 9, no children. 10. And now we don't add anything else. So now it's empty, and this while loop is done. It's escaped. Okay? So that was the traversal for breadth first search versus DFS. It's pre-order, which was vastly different from this, right? So this was all the ones from the same level, from the same depth, are grouped together, right? You're not going down the depth. It's kind of like you're grouping by depth. Does that make sense? Yeah, that's the difference, and it gives you a different ordering. Yeah.
So with that being said, like a question that it might ask you in an interview, what if you want to pop both the value and the depth that node is at?
Oh, well, we could say.
We ask them that.
Okay. I mean, I was thinking. You want me to ask them?
I know you.
Okay, guys. What if I wanted to print the depth of that node? What would I do? Maybe what you mean, like have a tuple of node? Oh, wait, am I giving it, Dan? Am I giving it away?
Yeah, that's part of it.
Sorry. Okay, how do I print the depth of this each node? Yeah.
You would have a tuple or
Okay, no.
Okay. It's incomplete. It's incomplete. I didn't give him the whole answer.
Yeah,
well, I'm thinking like a counter, but I
Yeah.
think that's really
Yes, exactly. So, go. Continue. What else did you have?
No,
in-
I just thought like a counter every time that you move a level down,
Yeah.
you increase the counter.
How do I know if I move the level down?
Yeah. it's-
How do I know?
There in that code,
Where would you
are we
put it?
moving?
Where would I put the counter? And where would I change it?
Whenever you're appending the
Yeah. Whenever I append, so when I append, well, actually, here, right? So I would put depth equals, are we going to say 1 or 0? So we start with 0, right? Right, we start with 0. Okay. because it's level 1. So 0, depth 1, depth 2. Okay. So where would I increment depth? When do I increment depth here in this while loop?
After 4.
Actually, let me think about this a little bit. I think it's a little bit more complicated than this.
Yeah.
No. Right? Because let's say we print out curve dot value
Yeah.
and then depth.
Yeah.
We have the value and the depth.
Right.
Then between the print and the for loop, implement depth. Increment depth.
After the for loop.
Before, it could be between print and the for loop or after the for loop.
So I'm just gonna do this. Yeah. Yeah, like that, and then
Actually, no,
this actually doesn't work.
do the tuple. I don't know why you didn't do the tuple. Make a tuple.
No, I'll just print it I'll just print them together. Print them together.
I don't think it's gonna work.
Yes.
Because node 2 is
Yes.
implement.
Yes.
Okay, let's see.
Yes.
I believe you.
Oh my God.
But he doesn't.
Okay. I was just printing them together. That's the tuple. That is the tuple.
No, that doesn't.
What? What? What?
Because when we are at node 2 in the tree, the depth is 1, right? The increment
Yeah,
is
yeah,
1.
yeah.
When we're at depth 5, the depth is now 2, but that's incorrect.
That's an incorrect depth. You're absolutely right.
Do the 2.
So yes, you're right. Wait, so then do you want me to actually print it here?
Q dot append tuple root 0.
Q dot append. Right.
And then every time you're appending the children, increment that value by 1.
Okay, so we see.
No, this one for sure.
Right. Oh, okay. Right. Right.
No, we'll do that next.
This is okay. It's tuple current depth.
Yeah, exactly.
Oh, wait, no, I see.
Yeah.
I see, yeah.
There we go. Yeah. There we go. So basically, it's the node, current node, and then the depth, which is in the queue, right? And then for each children, I append the child, and then depth plus 1, because it's an extra level down, and then that's gonna transfer when you go to the next root. So it's 0. Okay, so you're here, right? And then you added children, and the children had in the tuple, it was the value and the depth. These are 2. Then you go back here to 5, and 5 we said the depth was 1. So we preserve the depth level. We preserve the level when we go from 2 to 5, when we're popping left. All right? Does that make sense? Okay. So we get that. So that was BFS, traversal of a tree. It's a little bit different in a graph because you have to do extra things. But we have, how much? 5 minutes. So I'm going to leave it like this, actually. I was going to go over binary search trees next time. So that's what we're going to go over next Wednesday. Okay, yeah. So be sure to look out for the leak code questions. I have that handy. And be sure to check out, at least through live, the GitHub workshop we're having. And I'm mentioning it again. Really useful stuff. Know how to use GitHub. That's, project management stuff, version control software, all that good jazz. And so yeah, I'll see you all next week.